This is going to be another attempt to explain to draft science his biggest core misunderstanding between momentum and kinetic energy. First of all, draft science treats momentum the same way conventional science treats kinetic energy. For draft science, the direction in which an object moves doesn't matter. The values of momenta will always be positive. Whether an object is moving to the left or to the right after a collision, the momenta of both objects will always have a positive value. Whereas, for conventional science, the direction in which something moves is very important to determine the final momenta after a collision. When objects move in opposite direction, the momenta needs to be subtracted from each other. When objects move in the same direction after collision, momenta have to be added together. So far, I have provided countless of real physical experiments proving the case. However, every single one of them have been rejected and deemed garbage by draft science. Now, for kinetic energy, direction is in fact irrelevant. Kinetic energy will always have positive values and will always have to be added together, no matter in what direction objects are moving. So the first thing to understand is that there is a fundamental difference between momentum and kinetic energy. Even though they are both very closely related to quantity of motion, they have very different meanings. There are many things that can be said about this, so I'm going to subdivide this video into many small chapters. Timestamps will be provided for each chapter. Kinetic energy equals motion. When we talk about kinetic energy, we usually talk about things like heat, vibration, deformation, and sound. These are all things in which direction is irrelevant. So conventional science treats them as a scalar. Now, according to draft science, these are all vectors because these things also have motion in a certain direction. And yes, of course, that's correct. All of these are indeed motion, but at the microscopic level. Heat equals random kinetic energy of atoms/molecules. Vibration equals oscillating motion like a spring or sound wave. Deformation equals atoms getting displaced from equilibrium positions. And sound equals waves of compressed and rarefied air. So yes, it's all motion, but here is the key idea. These are all disorganized or internal forms of motion. Different types of energy like internal heat versus large-scale motion behave differently. Momentum is conserved as a vector, which means it tracks the motion of the whole system. And kinetic energy can be converted to internal energy, which stays in the system but loses directional information. So in a collision, for example, if some kinetic energy gets lost as heat, vibration, deformation, or sound, it's still energy, but it's now in forms that don't contribute to the system's net motion. So they don't have a vector. But momentum, that's only carried by the bulk movement of objects, and that always has a direction, so it stays vectorial. Why is kinetic energy not a vector? Because vectors represent net motion in space, motion of objects as a whole in a certain direction. Heat, deformation, and vibrations are all internal movements, often cancelling out in every direction. All these things do not influence the overall net motion of the object as a whole. So while yes, there is a lot of motion going on inside an object, jiggling atoms for example, they do not cause the entire object to move in a certain direction. For example, in a warm object, some atoms jiggle left, others right, so there is no net movement. In a vibrating string, one part goes left while another goes right, and that averages to zero. In a deformed spring, microscopic bonds stretch and compress, but again, no net direction. So even though energy is present, lots of motion, there is no overall vector direction for that energy, and that's why it's a scalar. Why we subtract momenta?
is minus 1/3, plus 2/3. And sensitive, we get 1/3 V1, and this one is plus 2/3 V1. That's the prediction.
Draft science thinks that subtracting momenta or canceling momenta actually means that you literally undo momenta, that you magically make momenta disappear out of existence. This is not really subtraction in the sense of removing something, it's just adding vectors with direction. We are adding vectors with direction. We are not subtracting to make it balance. We are simply respecting the directions. It's all about directions. And the amount of motion of an object or system in a certain direction can in fact cancel, because a system can, for example, move to the right, but at the same time move to the left, causing a net direction with a net quantity of motion. I have explained this in a previous video. A person can be inside a train moving to the right at 10 meters per second, and at the same time the person inside the train is moving to the left at 5 meters per second. The net velocity and the net direction of the person will be 5 meters per second to the right. Now we use positive and negative signs to indicate in which direction an object goes. We can use the negative sign when something goes to the left, and we can use the positive sign when something goes to the right. When we integrate this in this example, we get the net velocity and net direction equals positive 10 meters per second plus negative 5 meters per second. That equals positive 5 meters per second. The positive sign does not literally mean a positive value, or the negative sign does not literally mean a negative value. It simply means left or right. That's all. Momentum is not about how much is moving, it's about how much motion in which direction. Direction is crucial. Why is direction crucial for momentum? Because momentum is about motion that can push, transfer, or carry things. And that kind of motion is only meaningful if you know which way it's going. You can't just count how much motion there is, you have to know where it's aimed. If two things are moving with the same speed but in opposite directions, they can cancel each other's momentum. This directional nature is what makes momentum useful in analyzing collisions, explosions, and recoil. So let's elaborate on that. Predicting future motion. Momentum vectors give insight into how an object will continue to move in the future. By knowing the direction of momentum, we can predict the object's future path and destination. In Draft Science model, for example, direction is irrelevant, so his model cannot predict in which direction objects go after a collision. Analyzing interactions. In interactions between objects, such as collisions, the direction of momentum vectors determines the outcome of the interaction. For instance, in a head-on collision between two cars, the direction of their momenta determines whether they will move together after the collision or bounce off each other in opposite directions. What is a system? So now we have come to the point where we have to understand what a system is. Because in a collision with two separate objects, conventional science treats these two as one unified system or one unified object. But draft science treats them as two independent things. So, a system is just the collection of objects you choose to analyze together. So in fact, you define it. So it could be, a system could be just one card, or two colliding cards, or a ball plus the wall it hits, or a gas inside a box. Here's another description of what a system is. A system is simply the part of the universe you choose to focus on. A collection of objects that you define as being inside your analysis. Everything else is the environment or outside the system. So you get to choose the system depending on what you are studying. The system is the box you draw around what you care about. And that box could contain, once again, one object like a card, two objects like two colliding cars, a whole room of gas particles, or even the entire universe. Why do we treat two colliding objects as one system? Because it lets us use conservation laws like conservation of momentum. If no external force acts on the system, then the total momentum of the system is conserved. So when two objects collide, if they only interact with each other and no external forces like friction or walls matter, then the total momentum of the two object system stays the same before, during, and after the collision. This is why we combine them into one system. So again, you choose what your system is. It's a mental framework. In collisions, choosing both objects lets you use conservation laws cleanly. You treat them as a unified object not because they are literally glued together, but because you are analyzing the whole picture. So again, you could treat each card as its own system or both cards together as one system. If you treat each separately, you can't use conservation of momentum directly on one of them unless you know exactly how the other one interacts, because during the collision, each card experiences a force from the other, which is an external force from its own point of view. But if you treat both cards as one system, those internal forces cancel out by Newton's third law, and the system as a whole experiences no net external force, so total momentum of the system is conserved. This is why we treat them as one single unified object during collisions. It lets us apply powerful laws like conservation of momentum cleanly and correctly. And when you treat objects as a unified system, their center of mass acts like a single object. Example, head-on-head collision. Let's say you have two cards with equal masses moving towards each other. And let's say card 1 has a mass of 1 kilogram, moving with a velocity of 10 meters per second to the right, and card 2 also has a mass of 1 kilogram, and its velocity is also 10 meters per second, but moving to the left. The total momentum of the system is 0. Why is the total momentum 0? Because when we treat both cards as one system, the internal momenta cancel out due to opposite directions as seen from the perspective of the center of mass. Since both of the cards are the system that we are analyzing, we have to look at the center of mass of this system. So, the momentum is 0, but this does not mean there is no motion, obviously. It just means the motion of the whole system, as measured by its center of mass, has no net velocity.